Yeah, it's 10 o'clock, so we can start. Namaste and good evening, good morning, everyone. Welcome to today's webinar, and thank you so much for joining us. Myself, Dr. Pulkit Velani, I will be the host for today's session, and I currently lead the specification team at Midas IT Mumbai office, where our primary goal is to integrate the regional codes of India, the Middle East, and the Africa into the Midas software. So, as you all know, that today we'll be diving into IS 18168-2023 code, and the webinar is basically divided into four sections. First, we will begin with the opening remark from Mr. Manoj Mittal, who is representing IS 30. This will be followed by a keynote lecture by Professor Rupen Goswami from IIT Madras, which will last for about an hour. After that, Mr. Meet Tada from Midas will give us demo of about 15 to 20 minutes of Midas Gen software, which is specifically for building design, where IS 1893, sorry, 18168 is included. And finally, we will have a Q&A session to address any question you may have. So I kindly request all the attendee to post their question in the Q&A session of the platform, and we will get to them during the last segment of the webinar. So without any further delay, let me introduce Mr. Manoj Mittal. uh, Mr. Manoj Mittal is a seasonal civil and structural engineering consultant with over 39 years of professional experience. Proud alumnus of BITS Pilani. He specializes in the structural diagnosis, investigation, treatment, and retrofitting of distressed structure. Mr. Mittal actively contributes to various BIS technical committee and currently serves as the chairperson of SSD 06. He is also a visiting professor at the School of Planning and Architecture in New Delhi. His leadership extends to his role as a president of Indian Association of Structural Engineers during the term 2017 to 19, and then again in 2021 to 2023. Additionally, he has served as an independent director on the board of Power Grid Corporation of India Limited. I now invite Mr. Manoj Mittalji to give the opening remark for today's session. Over to you, sir.
Thank you, Pulkit, for the introduction, and good morning to all. And I very my warm welcome to all of you in this important webinar on IS 18168-2023 from code to software, which is being organized by Midas in association with IS Tactic. So I'm very happy that Midas took initiative and approached us to collaborate for this event. And as you know, IS Takti is one of the major, largest, and very active and vibrant body of structural engineers in India. And the capacity building and dissemination of the knowledge is our core objective. So I'm very happy that we have collaborated with Midas for this event. And I don't know if you are not a member of the association. I think I would encourage you to become the member also, because it will help you in networking and also get involved in the professional activities, various professional activities. So, as you all know, that steel buildings have many advantages actually over RCC buildings, and some of them are probably a high strength to weight ratio, speed of construction, flexibility, adaptability, recyclability, durability, precision, and consistency. So there are so many advantages over conventional RCC buildings which we do actually, which is very commonly used in India. But there are also some challenges like fire resistance, cost, thermal mass, acoustics, etc. So, but still, if you see the trend that the consumption of steel in India is increasing rapidly, and I'm seeing a lot of steel buildings are being made. So, I see a great future for steel buildings, and I'm very happy that BIS has also come up with the new standard, this IS 181682023, which is earthquake resistant design and detailing of steel buildings, which is an important standard prepared by BIS Technical Committee CED 39. So this is very, again, CD 39 is, I think, one of the best committee, I think, of the BIS. And Dr. Rupen Goswami is also part of that committee. And I think he's the best person to speak on this topic. He's involved into this code formulation. And I'm very happy that today he will be speaking on this standard. And I extend my special welcome to him in this session. So these days we cannot think of designing of structures without the help of the software. So all of us use the software, but somehow I feel that we as a structural engineer mostly do not understand what the software's capabilities are, what is the logic behind the software, whether it incorporates all the provisions which the code says. So I think we need to understand the software also. We should not use it as a black box actually. But at the same time, we also need to understand the code. I think this is the best platform, best webinar where we will learn about the code provisions, and also we will try to understand the software, which will be done by the demo in this webinar in the second part. So I'm sure this webinar will help us to understand the code and also the Midas software. Once again, welcome to the webinar and thank you so much. Thank you, Pulkit.
Thank you, sir. Thank you, sir, for your wonderful opening remark and for setting the stage for today's session. Now, let me introduce to our keynote speaker, Dr. Rupen Goswami. Dr. Rupen Goswami is a professor in the Department of Civil Engineering at the IIT Madras, specializing in the earthquake resistant design of structure and non-linear behavior of structures. His current research focuses on the seismic design of building and bridges, as well as the development of seismic design codes. Dr. Goswami is also the convener of the working group of steel building, which is CED 39, working group 10, where he plays a key role in shaping the standards and guideline for the design of steel structure. His work continues to have a significant impact on improving the safety and resilience of infrastructure, particularly in earthquake prone area. Professor Goswami, we are honored to have you with us today. I now invite you to deliver your keynote lecture on IS 18168 2023. Over to you, sir.
Thank you, Pulkit. Namaskar, Mithil Saab, and good morning to one and all. Uh, so, as while I share my screen, I'll say a few words. What Mithil Saab has said is very important. It's important to not just use softwares or use codes, but equally important is to understand the code and the softwares. As engineers, it is our responsibility to interpret it right and do justice to what it wants us to do. Before I begin, of course, it's also an honor to present this on behalf of all the members of the working group, as Dr. Pulkit mentioned, and of course, the larger committee of BIS. So what I intend to do here is, of course, we'll talk a little bit about this standard, but more than that, I'll try to give the background as to why you see the clauses the way you see them in the standard, and that will be the focus of my, this presentation. And of course, we'll see that in days ahead we will have to make some changes because of certain other upcoming revisions of the Indian standards that are coming up. Just like in reinforced concrete structures, we say that ductile detailing alone cannot make a structure earthquake resistant. Design is important. So is the case for steel structures, right? So with this particular point in mind, we BIS developed this new standard IS 18168, and it was published in 2023. However, the question arises as to what happens to IS 800. So let me reiterate first up that all design will continue to be done as per IS 800 for steel structures, just like we still continue to use IS 456 for concrete structures, except when earthquake resistant design comes. That is when for concrete structures we use IS 13920, and for steel we will be using this. So if you see this clause, it says the design and construction of steel buildings shall be governed by provisions of IS 800 except as modified by the provisions of this standard. This is a very important thing to remember. So IS 456, IS 800, these are the basic codes, and similarly for masonry, they will continue to be the design standards. However, additional provisions are going to be provided here. Now, when we design, of course, we start with the loading, and in for that we have this IS 875 series. By the way, this also is going to see a revision, and we are going to have much more items coming in here. But what I want to point out today is that it specified the loads other than earthquake. So there must be some reason why earthquake was kept out of that. So today, if we look at it, essentially we see that loads can be grouped into two broad sets. One is the force loads and the other is the displacement loads. This also will be something new that we will see explicitly stated in Indian standards in coming days. And one of the displacement loads is earthquake ground shaking effect. So what happens during earthquakes? There is nobody, or there is no load that is applied, but essentially the structure sitting on the ground is subjected to ground displacement, and it's in all these directions. So that ground shaking causes displacement at the base of the structure, and that helps induce force in the structure. Now, this force that is induced in the structure depends on how much displacement is imposed on the structure during the earthquake shaking. In this context, and particularly in the context of steel, we always bring in one item called ductility. Now, what is ductility? And in that case, we say some materials are ductile, some materials are not ductile. Essentially, if a material or a member or a system is able to undergo plastic deformation without losing its strength capacity, then we say that that is a ductile system or a material or a member. And we define ductility capacity as the ratio. One of the ways is to define the ductility capacity as the ratio of the ultimate displacement deformation to yield deformation. Brittle systems fail suddenly and therefore are not good for use, particularly during for a seismic application. So in this context, we all know perhaps the most ductile material that we have is structural steel, or steel, as right. It also has excellent modulus, Young's modulus, very high strength, very good ductility, and also very good energy absorption capacity, because during earthquakes a lot of energy is input into the system, and the system should be able to dissipate that energy. And so we believe that steel is an excellent material for resisting earthquakes. But in that context, there are other properties we must not lose focus of. One is called toughness, and the other is weldability of steel, because most of the time we will do, welded. We need welding to create steel structures. So we'll keep an eye on these two items also. Okay. Now, before I move on to the thing, let us see what has happened in the past to steel structures. Steel as a material is excellent, has very high strength to weight ratio, high modular strength, everything ductile. It's ductile. But we have seen time and again steel structures fail and collapse, not just not perform well, but fail and collapse in past earthquakes, right? And you can see that here a steel column, and you can see the size of it just got fractured. You can see fracture of steel, which we do not expect because we know that steel is a ductile material. Same case here, this is the base plate. You can see base. What you see here is fracture of beam to column welded connection. You can see the fracture here. and so on and so forth. So, if we look back and summarize the performance of steel structures in past earthquakes, we see that the major concerns have been connection failure, buckling, both local, global, as well as brittle material failure in tension, which is very, very surprising, right? And obviously, the outcome of all this is that steel structures have not performed in a ductile manner, although steel as a material is very ductile. The question is why, and therefore what needs to be done. So that brings us to the next, focus item of understanding earthquake resistant design. We said that earthquakes cause displacement at the base of structures. So if I look at a structure, let's say as a designer, I design the structure and I have different levels of earthquakes, meaning different levels of shaking, intensities of shaking, imposing different levels of displacements. If I do not want my structure to have any damage, I will have to design the structure to behave like this, essentially behave in a linear elastic manner. If that happens, when the very rare but big earthquake occurs, this would be the amount of, qualitatively, this would be the amount of lateral force that would be induced in the building, let's say, if it were to remain elastic. This is one option, one choice I have as a structural engineer. The other choice that I have is to design the structure to undergo damage but not collapse. So in this case, what will happen? From some point here, the structure will start losing stiffness and the strength will be capped here, but it should continue to undergo plastic deformation so that this displacement demand imposed by that rare severe earthquake is still met. So in this case, what is the maximum force that would be induced in the structure? If I allow the structure to undergo inelastic action, it would be this much. So if as a designer, if I look at both these options, obviously I choose the second option, which is design the structure to undergo damage during strong earthquake shaking. And that is exactly what we do when we design structures, normal structures, to resist earthquake shaking. So we set different, performance requirements, and we say that if the earthquake is small, minor, then there should not be any damage, because we do not want our structure to get damaged every day just because there is a small earthquake, right? If it is a moderate size earthquake, which can occur once in a while, then we will say that okay, some minor damage, so long it is repairable, is acceptable. But what we always want to ensure and must be guaranteed is that if that design severe rare earthquake occurs during the design life of the structure must not collapse. So this is where earthquake resistant design is different from all other design that we do. So when we design for instance, dead load, live load, we do not talk about allowing damage under dead load, live load, so to speak, right? So here, earthquake resistant design is different. It's a displacement loading scenario, and reliance is placed on the not on the strength alone, but on the deformation capacity. More importantly, the plastic deformation capacity, and therefore the ductility capacity. So that is why ductility becomes a very, very important aspect in earthquake resistant design. Now, this ductility is also in a way related to strength. And when you talk about strength, we will have to get used to one more term called overstrength. What does it mean? Essentially, when we look at a material, we specifically use the 5 percentile value as the characteristic strength. It also means that in most of the cases, if you go and look at the real structure, you would expect to find a higher strength than what is specified or what is used in your design calculation, right? So that is the thing. On top of that, we use partial safety factors, because we use limit state method of design. So we do not utilize the full strength of the material. We use in our design calculation lower strength, and so That is another aspect. Then when you use the load to design, we use higher load than what is expected most of the time. So we use load factors, partial load factors also. All these things put together leads to one simple fact, and this is very interesting and important to take note of, which is that in our design calculation, what we use as a design strength is not really the actual strength of the structure or a member or a connection or a system. The actual strength is much higher than the design strength, and that is what is called overstrength. Now the question is this a good situation or a not so good situation to have strength more than what we are thinking a system or a member has in terms of its design strength capacity? We will see why this is important to consider for the first time here. This additional strength is also something that is accounted for in design for earthquake resistant structures. So what we say is that, look, if the structure were not to have any damage, we should have designed it for so much force, the elastic force. But we said no, we will allow it to undergo damage, behave in a ductile manner, and therefore design it to have only this much strength. But then we do not design for that. We know that because of the certain things that we do as part of our design calculation, if I design the structure for this force, the structure will actually have a capacity higher, strength capacity higher than that. So we account for that also, and that is called the overstrength and the redundancy together called the overstrength in the system. And therefore we use our response reduction factor that also accounts for this overstrength, so that we design only for a fraction of the force that would have otherwise been induced in the structure if the structure were to remain elastic. So at this point, I want all of us to pause for a moment and understand that earthquake resistant design is looking for economy in design right from the first stage itself. Okay, it is not that earthquake resistant design is uneconomic. Right from the first step itself, it is trying to bring in economy in design, and therefore asking us to design, give earthquake resistant design codes give us a design force which is only a fraction of what we should have otherwise designed for if we wanted our structure to remain elastic. So economy is inbuilt in the philosophy of earthquake resistant design itself. That's very important point to remember. And based on all this, we see that our IS 1893 gives us, an expression to calculate so-called design force that would, an equivalent force to start our design, earthquake resistant design. And this is where we see the use of the response reduction factor. We know all that. But providing strength alone is not enough. Earthquake resistant structures should have certain virtues. One is good configuration. This is where IS 1893 comes in. It talks about irregularities that should be avoided, right? It talks about lateral stiffness in terms of restricting, for instance, in buildings, interstory drift under the design force level. Of course, strength comes in, but more important after this is ensuring adequate deformability, ductility, overstrength, redundancy, are desired collapse mechanism. And when all of these is done right in the right way, the structure would have enough energy dissipating capacity to resist that strong rare earthquake which is likely to occur during its design life. So when we talk about earthquake resistant design, it is not providing adequate strength capacity alone, but if we really look back at our design calculations, most of the design calculations are based on ensuring strength capacity. And this is where earthquake resistant design becomes different. And so simpler strategies have to be brought in into design standards to ensure that while still doing strength calculation, we ensure at least these are also ensured or guaranteed in the structure to the extent possible. Okay, I move on to the next one, which is how to therefore build ductile structures. The simple thing is, if you want to do ductile structures, the opposite of ductility is what we saw as brittleness. We have to avoid all brittle modes of failure. If we avoid all that, then we will be left with nothing but ductile actions and ductile members and ductile systems. So in steel structures, we know that all these different modes of damage and failure are brittle, and there are only two possible ductile actions that are there, which is flexural response in suitable sections. Essentially, I'm talking about plastic sections, and then shear yielding in properly designed sections can also be a ductile action. Everything else is basically brittle action, even in steel members and steel structures, right? And that is why we saw that although steel as a material is highly ductile, steel structures need not be ductile if we do not address this particular issue. So we said we'll allow damage to happen, but the question is where? Obviously, we do not want damage in soil or foundation. Definitely, we do not want the gravity load carrying members, primarily, let's say, in buildings. Most commonly, moment frames is something that we do in columns and joints and connections. So where are the locations where this ductile form of damage is permitted? That is where we say that, okay, in moment frames, flexural hinging at beam ends, ductile yielding in braces, or ductile yielding in shear links are only possibilities that we have. I'm sure all of us know about the chain analogy, which says that the strength and ductility of a chain depends on the strength and ductility of its weakest link. Very quickly, if I have to create a link, a chain, and I have two types of links. Let's say one of this color, this type, and the other is this type. What is the difference? Let's say I have two scenarios. I create two scenarios. In the first scenario, I have a large number of brittle links whose strength is more than that one single weak ductile link. Okay, that is one scenario. The other scenario is I make that one ductile link strong and the rest are all brittle links. The question is which option is better? The answer is that we need the ductile link to be weaker. Why? Because as the force increases in the link, the force remains same. So here, as the force keeps on increasing, at this level, the ductile link will yield and undergo plastic deformation. But until that time, the brittle links will not fail because they have higher strength capacity. But in the other case, the brittle links will fail at that level of force, induced force, and therefore the ductile link, although it is there, will not be able to help the chain attain ductility. So therefore, weakest link controls the behavior in any design. The second most important point here is therefore to understand how strong should the brittle links be. The brittle link should be, it is easy to say it should be stronger than the ductile link. But when I say stronger than the ductile link, what is the strength we are looking at? Are we looking at its design strength or are we looking at its overstrength? Obviously, the answer is its actual overstrength. So when we do earthquake resistant design, first we design the ductile link, then we have to estimate its overstrength capacity, and that based on that overstrength capacity, we have to ensure that the brittle links have strength capacity, design capacity higher than that. So this is an important intermediate step in strength design calculations required to be done for earthquake resistant design. We'll see a quick example for this. And this is where it is important to understand what is the overstrength. It is important to estimate that. We'll see this through a very simple small example. Let's say capacity design, how is it implemented in a steel moment frame building? Okay, these are the steps, doesn't matter. The first step is essentially you have created the model, you go to IS 1893, do all the things, do load combinations, calculate these forces, apply, do your linear elastic analysis, get your bending moment diagram for the frame. Okay. Now, this is where we take a decision. We said we will allow damage, but we will also say we will allow only these type of damages, flexural plastic hinge formation, and only at the beams, not this kind of a damage. We know this is called story mechanism, very bad. The structure collapses suddenly. This is called sway mechanism. We say that this is what we want. Very good. Now, based on that, then we go and actually design the beams. So what do I mean by saying, when I say design the beams, we do design as per IS 800. We calculate, we identify what is the cross section that is required to ensure that I get the required flexural capacity. Only thing here, we need to ensure that it is class 1 section and with certain modifications, as we'll see. So now that the beam section, which is supposed to be the ductile element, is chosen, the next question is the most important question. We ask, what is the overstrength capacity of this? So for instance, let's, for just for the sake of this discussion, if I say the design bending moment capacity or design bending moment was some 100 kilonewton meter, let's say, as an example, I come up with a cross section whose design capacity is 110. Now the question is that its actual capacity? The answer is no. So what is the overstrength capacity? The overstrength capacity actually depends on the actual material that is used, and also we need to account for possible strain hardening in the material. Remember, we use the design stress at this level. Fy by gamma m naught we use, but actually it can go well beyond that. How much strain hardening is possible? 10 to 20% is possible. Essentially, the flanges undergo strain hardening and gives extra strength. So that is the important part, and also the actual material strength will be higher. If we look at international practice, they recognize this long back. Okay, and this is why in IS 1893, IS 18168, we will see that there is a new addition called the material strength uncertainty factor. And for different grades of steel, or uh, grades of steel with different specified yield strength, you will see these values given. What does it mean? It means that that beam, which let's say had whatever 110 design moment capacity, its overstrength moment capacity can be as large as a factor for strain hardening, which generally we take as about 10%, a factor which is the material uncertainty factor, which is about 1.4 Ry, and then its nominal or characteristic plastic moment capacity Fy times Zp. So I want you to keep this in mind, this particular form. That is why in all over the standard you will see that this kind of a form you will encounter 1.1 times RYFYZPV. Substituting the value of, let's say, 1.4 for mild steel, what we get is the actual moment capacity can be 54% more than the nominal plastic moment capacity of this section, right? Now that sounds wonderful that we have so much extra capacity. Question is this good or is this bad? The answer is, don't forget, when that additional moment is induced in the system, there has to be an equilibrating shear equal to that, commensurate with that, that will also get induced in the system. And in steel moment frames, what is the next important component in the load path? It is the connections. If we do not design the connections, for instance, for this enhanced value of bending moment and shear, then obviously the connections would fail. So now you see that only the linear elastic analysis result was used to come up with the beam cross section, but after that, the connection design is not to be done based on the actual analysis results, but based on the capacity of the ductile element, and the ductile element in this case is the beam. So this is the process that we need to follow for design of the subsequent elements along the load path. we need to identify the load path, and along the load path we need to do. Very quickly, this is why also you will see that the code will talk about designing reinforced connections, preferably for moment frames, because if the most connections that we have do not account for these enhanced demand, both flexural as well as shear demand. And so, direct welded connections, for instance, would not be able to uh, you know, sustain or resist these higher demands. So this is how we do. We design a ductile element first, estimate its overstrength capacity, and that overstrength capacity actually becomes the demand for design of the next brittle element along the load path. And this process, where the design of the brittle element is not based on the original linear elastic analysis, but on the overstrength capacity of the ductile element from which it is getting the force, is called the capacity design procedure. I hope this looks familiar. And then this process is to be used for every, uh, between two members, or between a member and its connection, and so on and so forth. So achieving ductility in steel structures is about two things: the material nonlinear effect, which is yielding in steel, needs to be supported, and geometric nonlinear effect, which is buckling related issues and connection failures and other things, that has to be eliminated. If we do these two things properly, we will be able to achieve ductility in steel structures. So this is why we say that if you want a ductile structure or building, we need good connections to connect the members, individual members. We need good members that will not undergo premature elastic buckling. We need, for that to happen, we need good cross sections that are plastic enough. That means good plates with, that are not prone to elastic buckling. And of course, we need good material to begin with. Material wise, yes, we have good material. Steel is an excellent material, but we also need to ensure all these should happen. Then only we'll get a good ductile steel building that is earthquake resistant. Very quickly, material, we know all this, but this is where one more aspect comes into the picture. The same steel at low temperature becomes brittle. This is something we need to understand and keep in mind. So that is why we do one additional test other than the simple coupon test to determine the yield and the ultimate and the elongation capacity, which is called the Sharpe V notch, in test. And the CVN value is very, very important. So for instance, if you are building steel structures where the temperature is likely to go below 0 degree or -10 degree, -20 degree, we need to adopt a very different strategy of design steel buildings there than what we can do possibly, in a place like Chennai, where I'm sitting at currently, right? So this is an important aspect that we need to remember. Similarly, the same steel with different strain rates. Now, strain rate becomes important because earthquake shaking imposes very high strain rate depending on the system, the design, detail, everything. But essentially, that also reduces ductility. And that is why we have seen some of the fractures that we have seen earlier. So if you look at the structural steel that we have, what is required is at least a minimum of 27 joule of CVN Sharpe V naught test value. And that you will see that as we go for higher grades of steel, you will see that those grades of steel do not have this. They have higher strength, no doubt about that, but they do not have this toughness. And that is why it is risky or not preferable to use those grades of steel that do not meet this requirement. Okay. Also, of course, you can see the elongation capacity comes down as you go for higher grades of steel. So this is what was mentioned very nicely, that when you design steel structures, it's not just designing for normal ambient conditions, but also for cold temperatures, we need to see whether we have chosen the right steel to be functional at that temperature. And also, there is another aspect that we need to keep in mind, which is under fire conditions. So it's not just the ambient temperature that matters, but as a designer, when we design structures, we need to look at these extreme situations also and ensure that our structures are going to be not collapsing under such situations. The second very important aspect is weldability, and that is associated with what we call as carbon equivalent. Typically, more the carbon, less is the weldability, or less, or it increases. It increases more carbon, increases strength, but it reduces some of these aspects. So similarly, again, if you go back and see the lateral analysis table from IS 2062, you will see that the higher grades of steel actually do not conform to the requirement of an upper bound of carbon equivalent. And that is the challenge. This is not just with these steels, but worldwide, this is the issue. So that is why you will see that a very high grade steel is not used for seismic design, right? The last issue here is, the how the material, how the steel is manufactured, because it also depends on the grain size that is created. So slow cooling causes large grain size, leads to low strength. So what happens is, another very important thing is, when we choose a grade of steel, you will see that depending on the thickness of the material, you will see higher thickness material plates will actually have lesser strength specified in the standard. This is also something that we need to be mindful of, otherwise we usually forget, because in seismic design, very often you are likely to encounter pretty thick, thick plates. You will require thick plates because you need to ensure certain B by T, D by T ratio. So this is also something that we should not forget. So the same E250 grade steel can have yield strength, specified yield strength as low as 230, for instance, and not 250. So the point is, steel is a very good material, but it's not just the strength alone. We need ductility, we need hardness, and so there is only a small band of temperature and strength which works well for everything. And we should not cross these boundaries, this Lakshman Rekha, and go out. Then the same steel may not give you ductility. That's the point. And so therefore we have all these requirements coming up in the standard. Second, as far as section classification is concerned, we all know we do not like to have flange buckling, web buckling, and all these things. So because it reduces ductility capacity significantly. We all know these pictures that if we have slender sections, they undergo elastic buckling. Non-compact sections, they hardly reach the yield moment but do not have any ductility capacity. Compact section helps reach plastic moment capacity but again has limited ductility. And ductile or plastic section are the only one who have this, who reach not only the plastic moment capacity strength, but also gives you enough plastic rotation capacity. We all know that. But I want all of us to see this picture in a different perspective, which is how much of material utilization are we going to achieve if we use slender, non-compact, compact versus plastic sections. So in terms of utilization of the material, obviously it is only the class 1 sections that help utilize the material to its fullest extent. So that is why it is important that particularly for seismic design we use class 1 or plastic sections. And that is where you will come across a separate table in terms of limiting width to thickness ratio for different elements in different sections, and not all type of cross sections that are otherwise permitted by IS 800 are included here. By the way, even IS 800, that table will get revised in due time, and this table will also see some modification in the coming revisions. Member, we have seen we use plastic sections, but then if we allow the members to undergo lateral, for instance, lateral torsional buckling, then we are not helping again utilize the material that we are provided. So the members need to be adequately braced, and so for the first time you will see very specific requirements in terms of how to laterally brace these uh, elements so that you utilize the material in the form of material plastic hinges forming in these members. Connections are going to be very, very important in steel structures because we can design beautiful beams, columns, but if we do not connect them properly, then we will have trouble. And so connection design in all cases will follow the concept of capacity design that we just discussed. So here the connection between a beam and column will have to be designed considering the overstrength condition in the beam, for instance. Similarly, after the connection comes the panel zone. Panel zone design is very, very important because the panel zone is part of the column. So if the connection doesn't, you know, connection stays elastic, for instance, but the panel zone yields, you're essentially causing the column to yield and kink. And these kind of failures have been seen in the past because of excessive panel zone deformation. This is something that is very, very crucial. We have not been doing properly and we need to do now. So in if you look at an interior joint, we have three essential elements. Let's say we have the beam, the column, and the panel zone, assuming that we have taken care of the connection design properly. For the same configuration, we can have an entirely different behavior of the system depending on which element yields first. If I have column yielding first, followed by panel zone and beam, I'll have very limited strength and ductility capacity and deformability capacity of the frame. If I allow joint panel zone to yield first, which is essentially part of the column, remember, and then the beam, I will have some, it is possible to do this, but it will have limited ductility. But if you can allow yielding of the beam much prior to the yielding of the panel zone, that means the panel zone has to be stronger than the beam. If we follow that philosophy, then you can have a completely enhanced seismic performance of the same structure. So it is how we proportion these members, these components within a structure that's going to determine how the overall system is going to behave. And in terms of the final building, obviously we need to do global P-delta analysis because not considering that can severely overestimate its deformability and stability considerations. So we need to do all these set of things to get to a good ductile earthquake resistant steel building. Now, at the end, I'll quickly go through the specific provisions that are there in IS 18168 so that you can see. As I said, this was developed as a parallel code for IS 13920, which is for reinforced concrete structures. If you look at the table of contents, and this is something important I want to draw your attention to, you will see the first four, of course, are the standard items, scope, reference, terminology, symbol, and then we have the general provisions where all the material related aspects are specified. Then we have the next items, which are the members or the components, and we have beams, columns, beam column joint, column base, structural braces, and shear links coming in. And then finally we have the requirements. So these are these six items from serial number 6 to 11 are basically members or components. And then finally we need to put them all together to create the system, and that is where we have special requirements for structural systems, where three structural systems are presented for the time being, and within each you will see three very significant subsections called basis of design, member requirement, and system requirement. So when it comes to the member requirement, it will call back these one of these clauses as relevant, and it will give additional system requirements so that the individual members are put together in the right way to achieve a system that will be earthquake resistant. What are the three systems given here? Special moment frame, special concentrically braced frame, and special eccentrically braced frame. Now here, one very important thing that comes in, and this is very easy to do in steel structures, is that not all frames in a building need to be designed following this standard, or not all frames in a building need to be an earthquake lateral force resisting system. right? As a designer, we can choose these systems and then design them according. The rest of the system can be designed as, following IS 800 alone. Only thing is, how do we do this? It is not just that we assign these frames to be the lateral force resisting system. We have to ensure that they draw the earthquake induced force within themselves and perform the job that they are designed to do. So what matters here is stiffness of these frames. Okay, do not play with releasing end moments and things like doing things like that on the numerical model, on the software. As a structural engineer, we have to ensure that these designated frames have enough stiffness to draw the seismic force to them and then perform the ductile action that they are designed to do. Okay, that is very, very important. So it talks about the lateral force resisting systems. Typically, it is ideal to not have a common column, vertical member, to accommodate yielding of beams coming from two directions. You will come across these important words called protected zone, capacity protected elements, which are to be designed based on capacity design principle. Material strength uncertainty factor, we have already discussed why it is important and why it is there, and then give special requirements for demand critical build. So these are the things which are there in the code. Clause 5.2 talks about all the materials. It gives the material uncertainty factor, the required CVN value, and so on and so forth. 5.3 talks about section classification, as I said, which is different from what you find in IS 800. It is little more stringent, and if you really look at it, for instance, for rolled sections, currently IS 800 gives you a number like 9.4, and for welded sections it gives 8.4. Here it will come down to about 7.3, 7.4, because we need little more ductility capacity here for earthquake resistance. This is something different, that here we have an overstrength load combination coming. This overstrength load combination is important. It was there in IS 800 section 12 also, but this is to acknowledge that the actual strength that can be mobilized in a system is more than the design force that we have used so far in our design calculation. And what this requires is that when the actual overstrength is induced in the structure during that strong earthquake shaking, there should not be a collapse of columns, because they are the vertical gravity, the self weight carrying members, right? The column should not fail when that higher lateral force is induced, for instance, in the system, because then if the vertical members fail, you will we will see collapse of the structure. We do not want collapse. These overstrength factors will get revised a little bit as we move along. Then stability is given high importance in this standard, because any geometric nonlinearity doesn't help achieve ductility, and so we have a requirement for stability and stiffness. Sections I have already spoken about. For the time being, only doubly symmetric parallel flange sections rolled or built up are permitted to be used. And there are limitations in terms of slenderness, bracing requirements, and when we design the bracing, their strength, stiffness, and the connection all are given. Columns, similarly, are the most critical members, because they have to support the self weight, the gravity load all the time, even during and after the earthquake shaking. So therefore, there are special requirements for column design. You will see a limitation on the slenderness. This will come in time ahead for seismic zone 2. Similarly, we have requirement for bracing of the columns. And of course, splice design also is given importance. Beam column joint, three very important components: column to beam strength ratio, joint panel zone, and beam to column connection. All are important, right? We know story mechanism is bad, sway mechanism is good, because it helps achieve larger energy dissipation capacity, and we all know this result. A structure uh, can be made ductile only when we support a sway mechanism, and sway mechanism can be supported only by using strong column weak beam design. We do not want this column to fail first than the beam. Now, in this context, in steel design, there are three aspects. One is, of course, to eliminate, not permit story mechanism to happen. Second is whether to allow yielding of column or not. Obviously, it is undesirable. The third and the final issue is that the panel zone or design also is important, and that is where the amount of doubler plate that may be required later for the panel zone design also depends on the choice of the column section. So if you look at all of that, be considering all this, the beam to column or column to beam strength ratio is defined. Now, I want to just highlight one aspect. What this ratio essentially tries to do is it gives you a ratio in terms of capacity of the column to the demand that may arise from the beam. And this demand is obviously the overstrength demand, base demand. Now, in this case, the capacity of the column can be expressed in multiple ways. We can consider the actual, the interaction that is possible. The PM interaction is going to reduce the column capacity, or we do not consider that and simply say that okay, the plastic moment capacity of the column is the capacity. Now, the more difficult part is the demand coming from the beam. This demand, what you see this part, 1.1 Ry times this, is the overstrength flexural capacity. Plus there is an additional part which arises because for calculating this ratio, we look at the calculation at the central line. But the plastic hinge is forming here and there is a shear that is acting here. So that shear over that distance gives an amplified demand coming from the beam. So the point is, how accurately we quantify these depends or governs what this final number that you see in design standard should be. Okay, what is done, what you will currently find is that this number is stated as 1.4 without looking at all the details as to how the column capacity and the demand coming from the beam are calculated. Do not compare these numbers with any other number in any other code, Indian or international, because you have to compare apples with apples, right? So that is very, very important. Then clear design guideline is given in terms of how to design the panel zone. So how to estimate the demand on a panel zone and how to quantify the capacity of the panel zone are clearly stated in the standard. So that is what you see here in this clause 831. Essentially, what is done is it is kind of a towards strong panel zone design, but between balanced and strong panel zone. So the likely behavior is going to be plastic hinge formation in the beam along with limited yielding of the panel zone. Okay, and obviously beam column connection, fully restrained, reinforced or full strength connections only are preferred to be used, recommended to be used, and that is where you will see this design. In terms of detailing, there are finer issues given. The beam to the weld access hole that is usually used in welded connections also play a major role in terms of controlling the ductility of the section. So these details are also given. Column base, any type of column base is important, but for the time being, for the first time, it also talks about explicitly that any type of concrete failure should be precluded through design, right? That is also an important aspect. And now it is permitted, at least for building systems where we have enough redundancy, it is permitted to design and model column bases as pin column bases and not do a full capacity design there. Structural brace requirements are given, right? And their design strength, how to calculate their design, and their connections are all given. In terms of shear link, for the time being, only shear critical links are permitted to be used. Links can be flexural, combined or intermediate, flexural and shear, or shear. As of now, in the Indian standard, only shear critical links are permitted to be used, non-perforated solid sections. and not even HSS sections are permitted. So the design calculations and other things are given, right? And requirements of end stiffness are very important because you do not want buckling. So coming to finally the clause 12, which is structural system, you see this, and you will see basis of design, analysis, system requirement, and member requirement, and these are important things to follow. So for I'll not go into the details of it, but as I said, essentially it refers back to the clauses for for the respective members requirements, and then gives special additional requirements. In brace frame analysis, this is very important. It talks about uh, removing the compression brace which is likely to buckle, and use a post buckling residual strength, and then do that analysis so as to better estimate the demand coming on the tension brace. And these are the requirements given for the arranging the brace system. Similarly, for eccentrically braced frame, again, various configurations of eccentrically braced frames are possible. For the time being, only shear link which are part of the beam and in the middle of the beam are permitted. It is possible to have a shear link eccentric on one side attached to the column. Such links are not uh, permitted as of now, because their behavior is much more complex and analysis requires much more care. So since we are starting for the first time having provisions for eccentrically braced frame, only the simplest of the variety is given here. So I'll close with this now. Essentially, what has been observed, not just with steel structures but with all structures, is that earthquake effects on structures will systematically bring out the mistakes that we make in design and construction, and even the minutest mistakes. So we need to be a little more careful in what we do. Currently, three lateral systems, lateral force resisting systems, are provisions for these three are given. But we must also remember that moment frames are flexible, although they are ductile. Concentrically braced frames are stiff, although they are less ductile. And eccentrically braced frames are actually the one that are stiff as well as ductile. So remember the virtues. We need all of those. We need stiffness, we need strength, we need ductility, and overall we need good configuration, deformability, and so on and so forth. So it is time to now identify the strengths and weaknesses of the different structural systems also, and use them judiciously. And when I say braced frame, I typically like to show this picture as just as an example to say that bracing doesn't mean these single angle sections or tie rods and sag rods. Bracing means proper structural bracing. In time ahead, we will also bring in other systems like frame wall systems. Even in steel, it is possible. And then within brace frames, we may bring in buckling raised end braces and even the concept of structural fuses. These are in time ahead, we will see. So as you can see an example of steel plate shear wall, just like we are very comfortable doing reinforced concrete shear wall in reinforced concrete buildings, we should be able to come up with provisions and design and construct steel buildings with steel plate shear walls. So to summarize, there are quite a lot of expectations when you talk about earthquake resistant building. We need good materials that have enough toughness, that has enough strength, and also, of course, ductile. Right? We need sections that are plastic. We need members that are flexible enough to form plastic hinges, but not undergo geometric nonlinearity in the sense of buckling, right? We need connections that are stiff and strong, that allows the members to undergo to form plastic hinges. And in the structure, we need to keep an eye on load path and have redundancy. When we do all these things together, then we can expect to have earthquake resistant ductile steel buildings. Now, in time ahead, I'm sure this is something little ahead of its time, but we will see that depend realizing the strengths and weaknesses of the different types of lateral load resisting systems or frames, we will permit use of only few systems for certain cases. For instance, eccentrically braced frames seems to be the best system that we have, and we slowly have to start using them. But however, for normal buildings in seismic zone 2, you can see all systems are permitted. You would be wondering, why am I showing seismic zone 6? Because we have been revising our estimate of our seismic hazard, and we are doing it. Although I may say that this map also is likely to change, but I'm not showing that since BIS has not published it yet. But we are going to have 5 zones from 4 zones in time ahead. And one more change is going to happen. What you see today as IS 18168 will get subsumed into IS 13920. So in time ahead, we will have only 3 standards: IS 1893, that will help us estimate the seismic demand; IS 13920, that will help us design or essentially providing capacity to structures; and IS 13935, that will help us in assessment for repair and retrofit of existing structures. So new structures, when we are dealing with new structures, we will look at these 2 standards, 1893 and 13920. When we have to assess or look for the possibility of repair and retrofit of existing structures, we will look at the demand coming from 1893 and the IS 13935. IS 1893, 13920 and 13935 will have different parts, and buildings will come in as part 5, and within buildings there will be many these sections, and steel buildings will be the section 4 within part 5 of all IS 1893, IS 13920 and IS 13935. So this standard IS 18168, what you see today, will become section 4 of part 5 of IS 13920. That is the way forward that we are looking at. It's of course in the country designing steel buildings, and that too for earthquake resistant design, is kind of a new beginning. Although I might say that we have been having section 12 of IS 800 since 2007 published, right? But let's make a new beginning nonetheless. Let us understand the intent of each design clause, and that is what this webinar, I hope, will bring in a little more clarity on those. And we need to find our own strategies for implementation of this. All this, of course, BIS coming in and pitching in to develop new standards, we engineers trying to understand the standards, um, you know, companies like Midas coming up and developing softwares for all of these is towards having a safer built environment in the country. I'll stop now for now. I must thank BIS, of course, for doing all the work that they are doing, and then iStruct for providing us this platform today, and of course Midas for bringing us all together. Thank you so much. Jai Hind.
Thank you, Professor Rupen. There are lots of question answered, and I am sure there are more might have started after your presentation. So I request all the participants. I can see there are about 400 people are attending this. I request all of you to use a question answer session, because we intentionally kept this keynote part little, so that we can get more time for the discussion. So moving on the next segment, I would like to invite Mr. Meet Trada, who will be presenting the demonstration of the Midas Gen software with IS 18168 integrated into it. Mr. Meet is a senior technical support engineer at Midas IT, with experience in structural design for both bridges and buildings. He has played a crucial role in helping client implementing Midas solution and optimize their design process. With an MTech in structural engineering from NIT Surat, Meet has a strong academic background that complement his technical expertise. So, Meet, we are looking forward to your demo. The floor is yours.
Thank you, Pulkit sir, for the introduction, and good morning, sir. Good morning, attendees. So I will just share my screen. Uh, Pulkit sir, can you please confirm if my screen is visible?
Yes, yes, it is visible.
Okay. So we will start with the second part of the webinar, that is the seismic design of steel buildings with Midas Gen as per IS 18168 2023. So before jumping into IS 18168, I will just introduce our attendees with the Midas software portfolio. So for bridges, we have Midas Civil and Midas FENX. For buildings, we have Midas Gen and Midas Design Plus. And in mechanical, we have Midas NFX. And in for geotechnical, we have Midas GTSNX. So these are the softwares which are available for the building design, bridge design, and other stuff here. If I more talk about Midas Zen, that is particular for buildings, we can have different types of structures modeled and analyzed in the Midas Zen. So I will just summarize that buildings. So we have all types of buildings like RC building, steel building, composite building. It may be a plant structure, airport and hangars, stadium, arenas, gymnasium. Post-tension and pre-stress concrete analysis can also be performed in Midas Zen. Here, some are the examples of the structures, significant structures where Midas Gen was used for modeling or in some part of the analysis of building. So, with just moving forward with the presentation, we will come back to IS 18168. So, here I have summarized the list of the checks which has been incorporated in Midas Gen as per IS 18168 2023. First of all, we have load combinations. That is, additional load combinations prescribed by IS 18168 can be automatically generated along with the load combinations of IS 800 2007 in MyDesgen. We have also added the checks for special seismic checks for beam and column for SMRF system, and for beam and brace members for SCBS system. And at last, we have column strength to beam strength ratio check have also been added to MyDesgen. In the upcoming slides, we will be seeing the demonstration of each of these checks one by one. So we'll start with the demonstration part. So first of all, we will be going with the load combinations. So as per clause 5.5, we have some additional seismic load combinations, which are 1.2 dead load plus a partial shift factor into live load plus ocean factor into earthquake load. And the second being is zero point 0.9 into dead load plus ocean factor into earthquake load cases. So that both of the additional seismic load combinations can be generated along with the load combinations of IS 800 2007 in MyDesgen. We will just see in the video how we can do that. Here we will see how we can generate the additional load combinations as per IS 1816. For demonstration purpose, we have considered a model of a steel building with all the relevant loads applied under relevant load cases, and the model is analyzed. So we will move forward to load combinations. So go to the first tab, load combinations, and the steel design. We will use auto-generate to generate the load combinations. Select the design code as IS 800 2007. To generate the load combinations as per IS 18168, we will check on this option. And to assign the relevant ocean and partial safety factor, we will assign the factors under factors for seismic design. Here, all the load cases defined under earthquake and live load are shown in the drop down, and the relevant factor can be assigned to each load cases. Here you can see I have already defined the relevant factors of the load case, that is for earthquake. In X direction we have 2.5, for Y direction we have 3, and for live load we have 0.25. Click on OK, again OK, and the load combinations are generated. Here you can see the additional load combinations that are ASC are generated under special. Next, we will have the seismic design of beam and column for SMRF system. So in beam design, we have added section checks as per table 2, clause 6.1, slenderness check as per clause 6.2, and in strength checks, we have shear strength check as per clause 6.4.1. So we'll just move with the demonstration. Now we will perform the steel code check as per IS 800 2007 and considering the additional Samsung checks as per IS 18160. For that, we will go to Design tab, Steel Design. We will select the design code as IS 800 2007. To consider the additional seismic checks, we will turn on this option. Thereafter, we need to select the seismic load resisting system. So this system will be applicable to all the members of the structure. So for now, I will just select ordinary moment frame. Now, suppose my structure has two different seismic load resisting systems, that is SMRF and SCBF, both are present. Then I can apply individual members different seismic load resisting system by this option, that is seismic load resisting system by member. Here, I will just select all the members that are under SMRF. So I have already grouped those members. So I'll just select the SMRF members. I will select SMRF system from here and click on apply. Similarly, I will do that for SCP system. Now I will just activate the SMRF members and I will just select Beam, perform steel code check. So we just perform steel code check. Here you can see the result table where you can see the demand value as well as the strength values, and here you can see the check. And if you want a summarized report, we just go to graphic report. In graphic report, you can see there is design information, design forces, design parameters, and the results of the checks. So as it is failing in slenderness ratio, it is showing not good, and it is showing strength results here, and it is as it is passing in slenderness, it is showing okay. Now, if you want a detailed report, we just click on detail, where you can see the detailed report. Here you can see all the load combinations considered for the design and the information of the member. Here you can see the member was assigned SMRF system, uncertainty factor used for the material. Then here we have section classification where we have flange to width thickness ratio check as per 18168, which is here. Then we have web depth to thickness ratio check. Then we have slenderness ratio check as per seismic provision. And at last we will be having shear strength, where we calculate the shear demand of a member based on considering the double curvature of the beam, which is performed here. Similarly, we will check for column. So I will just close this. I will just select a column. Let's select this column and perform steel code check. So as in column, the design of the connected members is also considered. So all the connected beams are also designed as well here. So we'll just check the graphic report of the column. The graphic report will be as similar to beam like design information, number forces, and the checks or result checking results here. So we'll just go to the detailed report. So the detailed report on the column will be same as that of beam, but just checks will be different. That is, the forward will be the same. So here we have design information of the member. Then we have section classification. Then we have lens to web thickness ratio check as per 18168. Similarly, web depth to thickness ratio check as per 18168. Then standardness check as per 18168. But in column, we also perform axial strength, flexural strength, and the shear strength. So in column, so design of the connected members is also considered. So the axial demand based on the connected members is calculated and the check is performed as shown here. Similarly, the seismic demand is calculated from the connected member for shear. So based on that shear demand, the shear check is performed here. And similarly for the moment demand, it is the flexural demand. Flexural strength is performed here. So now we will focus on the beam and the brace design for SCBF system. So seismic checks have been added to beam and brace members, but for beam it is almost similar to that of SMRF system. So we'll just see the demonstration part of the brace member, where we have added the section checks as per table 2 and clause 10.1 and the slenderness check as per clause 10.2. Now we will perform steel code check as per IS 800-2007 and considering the additional sampling checks as per IS 18168. For that, we will go to design tab, steel design. We will select the design code as IS 800-2007. To consider the additional seismic checks, we will turn on this option. Thereafter, we need to select the seismic load resisting system. So this system will be applicable to all the members of the structure. So for now, I will just select ordinary moment frame. Now, suppose my structure has two different seismic load resisting systems, that is SMRF and SCPF, both are present. Then I can apply individual members different seismic load resisting system by this option, that is seismic load resisting system by member. Here I will just select all the members that are under SMRF. So I have already grouped those members. So I'll just select the SMRF members. I will select SMRF system from here and click on apply. Similarly, I will do that for SCPF system. Now I will just activate the SMRF numbers and I will just select beam, perform steel code check. Sorry, I think it has been playing same video, but the checks are similar to that of beam members. So we'll move forward with the presentation. So at last, we will be having the check for column strength to beam strength ratio as per clause 8.2, where we have tried to incorporate the ratio as mentioned by Rupen sir earlier. So we'll just move forward with the video
Now
demonstration.
we'll see how we can check the column strength to beam strength ratio as per IS 18160. For that, we'll go to Design tab, we'll go to Steel Design, then in Design code we'll set IS 800 2007, we'll turn on the seismic provisions check. Then to perform column strength to beam strength ratio at the roof level, we need to check on this option. If you don't want to check that, then we can just check off this option. So I will just click on close. Now to see the column to beam strength ratio, I will go to strong column beam check, then strong here. Then I will just select, let's check for 25 node number. I will just click on apply. So as you can see, we get the column strength here. We get the column strength for both local Y and local Z direction. Similarly, beam strength for local Y and local Z direction and the ratio. We can also change the limiting ratio from, for example, if I keep this as 0.5, it will check with respect to zero point 0.5, but as per our program, usually it should be 1.4. So I'll just check, keep it at 1.4. And as the ratio is less than 1.4, so it's showing not good.
So that is all about the checks that has been incorporated in MyDasGen as per IS 18168. So I will just take a moment to inform everyone that our team has been extensively working on development of other codes as well. So we are also working on the tall building code, that is IS 16700, and also we have been working on IS 1893 pre-draft. So I talk about the recent developments, so in the latest release we have been added the checks for tall building codes, and in upcoming development we have been extensively working on the IS 1893 2023 pre-draft, and many more such developments have been going on. So that is all from my side. And if you have any kind of questions regarding the software, or if you want some questions regarding the software or queries, you can always post them on the Midas Global Support, or you can always email us on india@midasit.com. And that's all. Thank you. Pulkit sir, over to you.
Thank you, Meet, for your wonderful demonstration. Uh, I hope participant had got the idea that some of the clauses are already integrated in the software and they can use for their design. So now we are reached to the final segment of today's webinar, the question answer session. So I would like to invite Professor Rupen to join us for this interactive session. And I think some of the questions are already answered, but maybe few of them can be taken up now. So over to you, sir.
Yeah, one very interesting and important question that comes up many times is that what do we do if design wind load governs the design? Do we still have to do earthquake resistant design detail? Right now, remember when you talk about the design seismic force, it is already a reduced value that we are looking at, right? So that's the first point. Second point is, so therefore compared to this reduced value, if the design wind force is coming out to be more, does it mean that the structure during its design life is not going to experience any earthquake? Answer is no. So it doesn't matter whether the design wind load is more than the design earthquake force or not, or in the other language, the way it is said is, it doesn't matter whether wind load governs or not. If the structure is in the of course it will be between zone 2 to 6, earthquake resistant design and detail must be done. So I saw that question, I have answered, but I thought this is one point that I would mention openly.
So let me read question for you, and then maybe you can take
Yeah.
up. So first question is from Saurin Pandyaji. As per IS 1893 Part 4 2024, Chapter 12 for Zone 4 and Zone 5 is mandatory. Does IS 18168 also specify the same? Does IS 18168 course criteria of seismic design of IS 800 and IS 1893? supersede. I think there is some typo error. So that is what he is trying to say. Which one will
Yeah.
govern, IS 18168 or IS 800 and 1893?
So, if you see the forward of the scope of this standard, it says it is about buildings, and IS 1893 Part 4 is about industrial structures. So, obviously, industrial structures are different than building structures, so to speak. So, therefore, what is currently written in this standard is that if required, guidance can be taken from this, but it is not meant for use in industrial structures. So IS 1893 Part 4 is getting revised, and there will also be as I said, IS 13920 Part 4 for industrial structures that will come up in due time, and that will be governing. But until such time, if any engineer wants to use some guidance from this standard, that is always permitted.
Okay. So next question is from Mr. Raghav. He's referring to slide 50, that why we are not considering strong brittle link plus strong ductile link.
If we provide both strong, and let's say both are almost close to equal, there will be little control on which one is going to see damage first, right? There has to be a significant difference to say that, okay, this is weaker, therefore this is the one that is going to yield first, and this is stronger, so that we need to have enough margin between the two. So if we do both, I'm assuming that you mean to say more or less equal strength, both ductile as well as brittle, then obviously we'll not have that control. We'll not be able to say for sure that the ductile one is going to see damage first, and therefore the system will behave in a ductile manner.
So the next question is from the same person, for referring to slide 111. What is the difference between the left and the right figure?
Oh my god. Slide triple. I don't know what left and the right figure. What is the. Oh, okay, okay. Okay, I understand. Let me just share that part. So the difference is only what we say here. We are talking about dual system. So here the difference is in the line thickness to denote that some of these frames may also need to be stiffened for it to perform well. So that is the whole difference. It's only in the stiffness and the strength of the things, nothing more.
Okay. Then next question is from Dr. P.R. Murthy. Why medium ductile sections are not considered?
Okay, very good question. As of now, if we see classically IS starting from IS 13920 1993, we have been following two categories of frames or systems, ordinary and special. So the decision as of now has been to continue with that process until we harmonize all the standards and finish this activity, right? So that is why we are going ahead with only ordinary systems and special systems. Now, looking at the recent results of the seismic hazard analysis that we have seen in the country, as of now, therefore, it is thought that we will continue with that and not bring in this intermediate or moderately ductile system or intermediate system as of now. Maybe in future it may happen, may not happen. I'm not sure. It would be the decision of the overall committee to take a call on that.
So next question is from Mr. Amit. He is asking why we cannot shift to advanced material such as stainless steel for 100 plus years design and no scrap loss.
That is, of course, under research. The only challenge is that with regular steel and particularly the lower grades of steel, we have enough of experimental results, if not in India, but at least abroad. So once we get to enough of experimental results, verifications and proof, then of course, it will also become popular in time ahead. But we need experimental proof in some form or other before we adopt any new technology.
Some of these are answered. Yes. Uh, Again, from Mr. Amit, the question is, sir, please suggest the elongation and corrosion allowance also to improve the infrastructure.
That should come in IS 456 and IS 800,
Okay.
and
Okay.
I'm sure it will come.
Okay. And then next one is next question is from Rajendran, Mr. Rajendran. What is the rational explanation behind the limitation given in clause 1.3?
What would be the clause 1.3? Oh, clause 1.3 is about the choice of structural system for different zones. As I mentioned, moment frame particularly, let me, instead of going through the whole thing, let me say this. Moment frame is very flexible, although it is ductile. So moment frame systems and particularly steel structures are inherently flexible compared to reinforced concrete counterparts. So therefore, in higher zones, the displacement demand will be very high, and so we are likely to see very high second order effects, P delta effects, and so on and so forth, which is not good, and therefore use of moment frames in higher zones is prohibited. That is the essence of the whole clause, right? And we are going to see this coming in even in reinforced concrete structures. Moment frame, that is why in 2016 revision of IS 1893 and 13920, we saw that use of structural wall became mandatory, right? Precisely for the same reason that we need stiffness. We cannot utilize or ductility alone if we have very flexible systems. So for steel structures, for steel buildings, brace frames are required, and within the two brace frames, it is the eccentrically braced frames that gives you stiffness and ductility both. And so for higher zones, it is the use of eccentrically braced frame is recommended.
Sir, the follow-up question by the same person is, can you please compare the Euro code and ASC code for the same? Any comment for that?
So all these comparisons and everything was, of course, it has been done at the working group level, at the, the main committee level. But the point is, there is no end to looking at other standards and, comparing. India has its own unique situations, challenges, and we have to develop our own standards and, improve our own practice. So while this comparison and review is always done, but once the standard comes out, I think we need to first see how best we can start implementing the standard in our daily practice.
Next question is, drift check should be for what load combination after response spectrum analysis?
Drift check. So now, if we look at what is going to be coming up, the earthquake force is going to be not going to have uh, a load factor of 1.5, 1.2 that we have today. So it will be clearly stated as to what force, what magnitude of force to be used for that particular interstory drift check. It will be there precisely.
So next question is from, I think, Mr. Manav. He must be student. He is writing, sir, can you please explain what exactly is a plastic hinge and why is it important?
Wow, okay, that's interesting. So plastic hinge basically is that when you have a beam and you start, applying moment, bending. We follow Bernoulli's hypothesis. We say that strain diagram is linear, and associated with the strain diagram there is a stress diagram. So when the strain at the extreme fibers, tension and compression, let's assume a doubly symmetric section, reaches the yield strain, the material yields. That is what is called the yield state. So the maximum stress at the extreme fibers reaches Fy, let's say. Now, if I go on increasing the curvature further, what will happen is the steel material will start going on the plateau. So more and more fibers across the depth will start reaching the yield stress. And hypothetically, we reach a rectangular stress block, which is not the real stress block, by the way, where we say that the entire cross section has yielded. And at that stage, we calculate what is the maximum moment capacity that is generated and what is the curvature that is imposed. So that state is what we call referred as a plastic yield state. That means most of the cross section along its depth, across its depth, has reached a yield value, yield stress value of Fy at least.
Uh,
So,
now,
and just to complete that, just to add to that, so when this happens, essentially the material is already in the nonlinear state, and in that state, if we do reverse cyclic loading, it basically gets into inelastic energy dissipation, and that is what we want, because the earthquake is feeding energy, and if we take the material into the inelastic range, we will have hysteresis, energy dissipation, and that is very efficient to dissipate the energy that earthquakes are feeding into the structure during the shaking.
next question is from Mr. Manoj. He is asking, many times Chapter 12 of IS 800 was not considered for costing by PEB vendors and client during DPR slash tender stage. This leads to a major cost impact in EPC contracts. Please advise the applicability of this code zone wise and based on the type of structures.
So all Indian standards are applicable, provided based on your DBR or DPR, whatever, right? Now, I don't think today we are discussing the standard. We are not discussing the practice in the country. So all I would say is that we need to improve our practice and then follow Indian standards to the best possible way. And we need to improve that. There is no doubt about that.
Okay. I think next question is industrial structure is under this code or not?
I said no, technically no, because there will be a new standard only for industrial structures. But until such standard comes up, you are free to
Hmm.
follow IS 800, existing IS 800, and if you want to take guidance from this standard, you are free to do that.
I think this is different but relevant to steel structure, so I am reading this. Damping ratio for steel structure, what is that? Is part 4 and part 1 1893 have different values?
No. So, I understand the context of the question. So, in 2016, when IS 1893 was revised, the damping, the correction for damping was removed. The intent was to say that for the purpose of design, for the purpose of design alone, all structures will be designed considering 5% damping. Why should steel structures be penalized by making steel structures be designed for 2% damping? That means 40% more force, right? Now the argument is, but what is the actual damping? The actual damping is neither 1% nor half percent, not 2%, nor 5%, not 10%. It depends on the level of shaking, and it is an instantaneous value which cannot be estimated or cannot be recommended by any standard. So what we assume is that for design, all structures will be designed for considering 5% damping. But for assessment, and if the design requires no damage or limited damage philosophy adopts that, then of course structures can have different damping. So that will come in separately in the assessment standard, or even for design of different types of structures, because all structures need not adopt full damage, full ductile actions. So when that is happening, yes, we can, you know, go ahead and use different values of damping. But when the philosophy is uniform across all structures, particularly at least for normal structures, where we expect damage to happen, then there is no reason to segregate between based on the materials and say this type of structure will have this damping, that type of structure will have that damping. No, let us make a level playing field for all types of structures to be designed at the same level, and that is using 5% damping.
Thank you, sir. Now, next is mm, is dual bracing system assuming only some frame as moment resisting, that is only that will take earthquake load? What if that frame is also taking lateral load?
Earthquake induced force is lateral force. So yeah, if you have couple of frames in, let's say, each direction that is stiff enough, they are going to draw the seismic force into them. So that is why I've said this, probably this is the third time I'm repeating this. Stiffness is very important. We need to make these frames stiff enough to draw the site induced inertia force towards them, and then the rest of the ductility deformability story continues. So it is very important for that.
I think this question is coming repetitively, like industrial structure, plant structure like power plant need not follow the provision of this code. So, sir has answered. So, I think this is again from student. I am happy that there are a lot of student and they are asking question. So, though it is minor, but I want you professor to give answer. If in the
Uh,
pushover curve there is a drop after some displacement, then after that there is a smooth curve, then what it represents?
So it is a local component damage. It has reached its, you know, ultimate deformation capacity that you would have given as an input, and that is why you see that there is a, you know, drop. But that is not you know, significant enough to cause a global failure. That is what it possibly you know, denotes.
Mm, okay, there are a lot of questions. Okay. Post earthquake safety is critical. How does IS 18168 ensure that steel structure remains serviceable after a seismic event, particularly in terms of residual strength and functionality? Are there provision for post event inspection or retrofitting?
So the first thing is the statement we need to improve a little bit, saying that all sizes of earthquakes, if we are expecting our structure to remain serviceable, then we have to design the structure to remain elastic, even for the design level earthquake, which is not the practical way of doing things, at least normal structures. So that is why in the coming days, when IS 1893 gets revised, we will see different categories of structures: normal structures, important structures, um, you know, critical and lifeline structures, and even spatial structures. And if you now compare, if you when we design these different types of structures in the same zone and compare their behavior for any one specified level of earthquake shaking, we will be able to see different performances. Now some may remain serviceable, some may not remain serviceable. That depends on the design, how it is done. So all structures, particularly normal structures, need not remain serviceable following a major earthquake. That is why we say we are going to allow damage to happen. Only thing we do not want is collapse. So we do not want life loss, we do not want collapse, and that must be guaranteed. And so the standards today are trying to achieve that. The aim is to ensure no life loss, no collapse. Once we achieve this, then we can start working towards improving our own benchmark and say, okay, now we have achieved no collapse, no life loss. So now let us start improving the performance in terms of keeping our structures, immediately occupiable and so on and so forth. There was a second part of the question. I forgot. What was the second last part of the question?
Uh, Actually, I
Oh yes, assessment. So as
yes,
I mentioned,
assessment and
at the
retrofitting.
So there are three standards that are coming up: 1893 series, 13920 series, and then finally 13935 series. So 13935, part 5, which is for buildings, and let's say section 4 of that will talk about assessment of steel buildings. Part 3 will talk about assessment of reinforced concrete buildings, and so on and so forth. So it will come there.
One of the question is like we are talking about the strong column, weak beam, but what if foundation is not designed properly? What will be
Of
the
course, foundation
implication?
has to be designed properly. Very good, very important question. Very good question. Foundation has to be designed properly, and you will see in 1893 revision, it will be explicitly stated.
Hinges are forming at the base as per desired performance. Please explain its advantage. Don't it will lead to collapse?
Yes, you are right. So every structure has a limitation. The limitation is it has to collapse. So we are trying to find out at what level will it collapse, and just prior to collapse, how does it go through the entire sequence. So we do not want the hinges at the base to be the first hinges to form in the structure. That is one way of looking at it. Or you design the pin, the column bases as pin base, so you don't worry about forming hinges there anymore. Then the rest of the thing is within the, whether it is happening within the beams or in the columns. But if we are going to have a really strong earthquake and the structure is going to collapse, what is the mechanism that's going to unfold before that final collapse happens is what we are trying to understand by doing these kind of analysis. And in that we expect, if at all the column bases have to form plastic hinges, they should be the last ones to form.
So next question is, what if the structure built earlier to IS 18168 are passing with IS 800, but the connections, if checked with new design code 18168, are failing? Note the structure is already built.
Okay, so this is a situation that we are going to face not just with steel buildings or steel structures, but all structures. As we revise the standard, as the hazard level changes, every building may or may not conform to the new requirements. So does it mean that everything has to be changed? Answer is no. Answer is no. So clearly, one thing is stated: unless there is a occupancy change, or you are doing an extension to the building, or if it is a very critical structure, a government structure where the decision will be taken, all the buildings need not be repaired and retrofitted, right? However, as the owner, if you wish to do that, you are always welcome and you are free to do upgrade your structure, but it is not mandatory. Then what will happen is, I mean, it cannot be made mandatory. It is never made mandatory anywhere, but because all the existing structures would have to be upgraded, then that's not possible practically. So if the connections needs to be upgraded, and if you, as the owner, if you think that it should be done, nobody will stop you from doing it. Please do that.
Next question is, to calculate time period for a structure, can we consider time period of stiff frame alone? I think it is referring to when we have very few frame are resisting lateral load. Maybe I think
No,
it is referring
no.
to that.
So today, if you look at the configuration related issues, most of the time we require three-dimensional models to be created. So once you do that, it is not of the steel frame or the flexible frame, it is of the system as a whole, the building as a whole. So the natural period should be of the building as a whole. And obviously in that, the stiffer frames will dominate, will govern that result.
How effective are advanced material like shape, memory, alloy, and high performance concrete in enhancing seismic resilience?
Very broad question. Uh, all I would say at this stage is, of course, these things have to be looked in very carefully at the respective committees of the Bureau of Indian Standards, and they will be looked at. Only thing that I will highlight today is that we need experimental verification, a proof of their performance, not just at the material level, but as I showed, material, section, member, connection, and structure level. Without these proofs, it would be very difficult for any organization like BIS to come up with a standard and permit use of those things.
Uh, what provision does the code suggest to incorporating passive energy dissipation devices or seismic dampers in steel buildings?
So we already have IS 1893 Part 6, which is for base isolated buildings. So this standard is already published, and there will be standards coming up with other energy dissipating devices. That is under preparation. Will take a while to get published. But base isolated building, the standard is already published by BIS.
Think any suggestion on a good reference book for whatever topic we have discussed? Can you recommend anything, sir? That is what a couple of students are asking.
Don't confine yourself to books from one region. Read all books on steel, seismic design of steel structures, the seismic design of concrete structures, seismic design of masonry structures across the world. You will find a lot of good books.
Uh, so I think there are a lot of questions, but we have to respect the time, and we have to stop here. Maybe looking at the question, maybe we we will come up with one more session of Professor Rupen. So uh, I just want to share my screen once. So like as we like the main objective, one of the objective of this uh, webinar was that as recommended in NDMA April 2007 guideline, that there should be a zero tolerance to avoidable deaths due to earthquakes. So we have already entered into 25th year of Bhuj earthquake of 2001. So I think collectively, be it academic recommendation in academia or government or wherever we are, if we do our tiny part, I think we will surely reach to this goal and contribute to the nation building and come up with the resilient society. So with that, I I thank first and foremost a big thank you to Professor Rupen for delivering such an engaging and thought-provoking keynote address. Your expertise and insight have provided us with a valuable knowledge, and we are deeply grateful for your time and effort in joining us today. I would also like to extend our sincere thanks to Mr. Manoj Mittal for giving us the opening remark. Your word sets the tone of the event, and your support is truly appreciated. And I also thank Mr. Meet for representing Midas and showing the demo of the software. And lastly, I would like to thank all of you, our dear audience, for your active participation and engagement throughout the webinar. Without your involvement, this event would have been meaningful. Once again, thank you everyone for making this event a memorable one. We hope to see you all again at a future session. Have a great day ahead. Thank you. Thank you so much.
Thank you.